All right. So, here's what we want to do. We're going to start chapters 14 and 15, which is a look at equilibrium in aqueous solutions. There are two big sort of categories we're going to talk about when we talk about aqueous equilibrium. One has to do with acids and bases, and one has to do with precipitation. But they're all fundamentally the same equilibrium problems that we've been doing. We're just wrapping them up in different packages. Okay? So we're going to expand sort of the chemistry around the core idea of calculating equilibrium for chemical reactions that happen forward and backwards. What's been going on is Becky and her big brother Billy like to fish in their local pond. But they've been seeing some problems with the fish. Fish have been sick, had some skin lesions and stuff like that. It's been pretty disgusting. And they think that there might be a problem with the pond water, that the pond might have its not enough acid or too much acid. They're not sure. So they need us to understand what's happening when we have acids involved in aqueous solutions, so that we can go along and see how we can make sure that the pond will stay nice and healthy so that they can continue to fish. The key thing that we have to understand, we've talked about acids before. Remember that we have talked about acids that are strong versus acids that are weak. We've talked about the Arrhenius definition of an acid versus the Brønstead-Lowery definition. Arrhenius definition is a simpler, produces hydrogen ions. Brønstead-Lowery is the idea of a transfer of a hydrogen. Acids give off, bases take in hydrogen ions, protons. But the big thing that we need to add to this idea is that we need to start to think about acids and bases and the way that they behave in water, because of the way that they dissolve, as really being equilibrium situations. If we have an acid, some generic acid, HA, dissolving or reacting with water, okay, so this is the acid basically dissolving into water to produce the hydronium ion and the conjugate base. Remember, we talk about acids as conjugate base, acid-base pairs. Okay? So here's our acid. We recognize it as an acid because it loses this hydrogen to the water. Okay? And so then this A, the A minus, the conjugate of our acid is a base, because if we look at the reverse reaction, what we see is the A minus gaining a hydrogen to form HA. So this is an equilibrium situation. We can write out the equilibrium expression. Remember, that's the K equals concentration of the products over concentration of reactants. The only thing we put different, the only sort of specially fun thing here is that we call this K sub A, Ka. And that A there stands for the acid dissociation constant. This is the equilibrium constant for an acid breaking apart. And we always write it as the acid on the left breaking apart the products on the right. Now, we can simplify this reaction. We frequently do, because while we know that in water hydrogen ions don't float around by themselves, that they form the hydronium ion, a lot of times we like to leave that out. And since the water is a liquid, and we know that we leave liquids out of the equilibrium expression, so there's no water in the equilibrium expression, we can go ahead and simplify this by dropping the water and changing the hydronium to a hydrogen ion. If we did that, the only change we need to make is change this hydronium into simply a hydrogen ion. Now we have our acid dissociating. Okay, our acid dissociation constant. This is still an equilibrium process. It's going to be governed by a Ka value, still an equilibrium process. Now, what we want to think about for a sec is we want to talk about, hey, let's see how this actually happens. HCl, hydrochloric acid, we know that that's a strong acid. What does it mean when an acid is strong? It completely disassociates, and the conjugate base is very, very weak. Okay, those are both true. Okay, so strong acids completely break apart. They completely disassociate to hydrogen ions and chloride ions in the case of hydrochloric acid. So if we were to think about this equilibrium, we can write the equilibrium. what's going to happen to this number here? It's going to be really small. In fact, it's going to approach 0. And if this number approaches 0, what's going to happen to the Ka value? It's going to blow up. It's going to approach infinity. Okay? And in fact, if we pulled out the Handbook of Chemistry and Physics, my big reference book, and we turned to the section where they list Ka values for acids, and we looked up hydrochloric acid in this big table full of Ka values for different acids. For hydrochloric acid, for any strong acid, what you see in there, what they write is very large. It's not a number. They literally just write very large. Because it's so big, and this number is so small as to be essentially unmeasurable. You have a couple of molecules, maybe. Okay? And so what happens is this reaction essentially isn't really in equilibrium, and it really just runs to completion. But if this was a weak acid, as most acids are, you memorize the 6 or 7 common strong acids, most acids are weak. This acid breaking apart and its equilibrium expression, the Ka value is not going to be very large. It's going to be very small. It's going to actually be significantly less than 1. Common weak acids like ethanoic acid, 10 to the negative 4th Ka value. Okay? So very common for acids to have Ka value significantly less than 1. We can then really have to think about doing equilibrium calculations to calculate how much hydrogen is in the solution. And that's the key driver of a lot of chemistry. What's the concentration of the hydrogen ions? Okay? So we need to get at this hydrogen ion concentration. That's the key thing that would be hurting our fish. That's the key thing into how potentially dangerous some solution is. But just before we jump into that, we need to talk a little bit more about some names, some vocabulary. Okay? We need to talk about polyprotic acids and amphoteric substances. Poly means many, more than one. Protic, protons, more than one proton. So, sulfuric acid, H2SO4, will produce hydrogen ions, and then it'll have some Ka value. This Ka value may very well be very large. Okay? So, Ka1, we call it, for the first hydrogen that comes off. But this reaction doesn't produce just hydrogen, it also produces hydrogen sulfate. And hydrogen sulfate itself can undergo another reaction. And that hydrogen sulfate can produce a second hydrogen in solution with a different equilibrium constant. The second constant, typically much smaller than the first. 5, 6 orders of magnitude, not unusual. So this second Ka is going to be much smaller than the first one. If somebody asks you to calculate all the concentrations in here, we would have to go through and do an equilibrium expression for the first one based on the Ka value here. And then we'd have to take the results of that to be our starting values. We'd have a starting value for hydrogen sulfate, we'd have a starting value for hydrogen, and we'd have to do a second ice diagram equilibrium problem. Okay? Polyprotic acids are acids that can produce more than one hydrogen. Each hydrogen that it can lose has its own separate Ka value. Typically the hydrogen, the Ka values get smaller as the charge on the whole molecule increases, because this next hydrogen is progressively harder and harder to pull off. Polyprotic acids are acids that can lose or produce more than one hydrogen. Each hydrogen loss, each step, has a Ka value associated with it. Now, the second word up here is amphoteric. And an amphoteric substance is a substance that can function as both an acid and a base, depending on conditions. Hydrogen sulfate. Okay, if you look at this reaction, the second reaction, hydrogen sulfate in this forward reaction, HSO4, what does it do during the forward reaction? It loses a hydrogen to form sulfate ions. So if the HSO4 is breaking apart to produce hydrogen ions, how is it functioning in this reaction? Acids produce hydrogen ions, so yeah, it's functioning as an acid. Now let's look at the first equation. Here's HSO4. Now let's look at the reverse reaction. If we think about this reverse reaction, what is the HSO4 doing to turn into H2SO4? It's gaining a hydrogen, and that's the definition of what a base does. So HSO4, hydrogen sulfate, can function as an acid or it can function as a base depending on the situation. We say that hydrogen sulfate is an amphoteric substance. Amphoteric means that it can function as an acid or a base. Another classic important example of an amphoteric substance is water. Okay? Water is a substance that will react with itself where one of the hydrogens gains a hydrogen and one of them loses. In other words, these two hydrogens can bump into each other and one of them will lose a hydrogen to form hydroxide. One of them will gain a hydrogen to form the hydronium ion. We can essentially rewrite this. Another sort of simpler way to rewrite this is to say that water will autoionize. Water will break down on its own and produce a hydrogen and a hydroxide, an acid and a base. Water is amphoteric. This equilibrium, this autoionization of water, is super important to any kind of work that we do around aqueous solutions, particularly around acid or base aqueous solutions. Because this equilibrium is always going to be happening in water. So if we add an acid that changes the hydrogens, it's automatically, because of this equilibrium, going to change the hydroxides, and we'd want to be able to do calculations around that. So we give this equilibrium, we give this reaction a special value. We talk about its equilibrium constant, and we give it K, we call it Kw, where the W, of course, stands for water. So this is the equilibrium constant for the autoionization, the self-ionization of water. What is this Kw going to be equal to? Concentration of hydrogen and hydroxide. Do I divide by the water? Nope, water is a pure liquid, we leave it out. So Kw equals the concentration of hydrogen ions times the concentration of hydroxide ions. At room temperature, that's 1.0 times 10 to the negative 14. Yep, this doesn't happen very much. Now we know that these two values, because of the stoichiometry, have to be the same. So in pure water, what is the concentration of the hydrogen ions? Square root of 1.0 times 10 to the negative 14. Square rooting this exponent is like dividing it by 2. So this becomes 10 to the negative 7. 1.0 times 10 to the negative 7, 1.0 times 10 to the negative 7. The hydrogen and hydroxide are equal. That's our neutral solution. That's pure water. Okay? So what we want to do is we want to keep that in the back of our heads. We've got to think about this, because anytime we're dealing with an aqueous solution, particularly with acids and bases, hydrogens and hydroxides, we have to be aware that there's water in there as well and that this equilibrium is happening. And that could be useful to us. Now, in our investigation of the pond, in trying to figure out what's going on with the chemistry of this pond, why is the pH balance off, we find that there is a source of contamination. And we did this sort of water quality stuff on Monday, right? And there were pipes coming in, and some of them were dripping, some of them were drainage, some of them we don't know exactly what. Hopefully, if you had your site had some pipes coming in, you tested them. That pipe water coming in frequently is different than the creek water that's already there. Not necessarily a bad difference, just different. And so when we did our study of the stream, we found that there was some runoff, some residues coming from a nearby glass factory. Okay? We want to make sure that the glass factory, the residue, the waste coming from that glass factory isn't affecting the pond. Or if it is, we want to make sure we know how it is so that we could offset that, so we can clean it up. One of the things that is really important to biology of of an ecosystem or a person or an organism is the pH. Okay? And you have all heard and seen these words before. pH is something that you should have talked about in middle school. I know that you have heard it on TV. You can talk about the deodorant that is pH balanced for a woman, right? You hear these kind of phrases on TV. They talk about shampoos and conditioners and deodorants as having certain pH, right? If you have a fish tank or a pool or a spa, you need to check the pH, okay? pH is simply a way to measure the hydrogen ion concentration. It's a logarithmic scale so that you can express a really wide range of concentrations with very few little numbers, okay? So pH literally is simply defined as the negative log of the hydrogen ion concentration. So that means that a factor of 10 change in the hydrogen ion concentration will drive a factor of 1 change in the pH. So the log, this is log base 10. So if we change the concentration of the pH by a factor of 10, so it goes from, say, 1 to 0.1, that changes the pH value not 10 times, but by 1. So a pH of 1 would be a hydrogen ion concentration of 1, but a pH of 2 would be a hydrogen ion concentration of 0.1. Right? So it's a 10 times change in concentration drives a change of 1 value in pH. So if we look at the pH scale for a sec here, pure water, again, concentration of hydrogen ions, 10 to the negative 7th, pH is 7. That's pure water. We go more acidic, the pH value goes down as the concentration of hydrogen ions goes up. Again, there's a negative log value there. Okay? So, milk is slightly acidic, about a 6.5 pH. Vinegar, okay, pH of 3, concentration of hydrogen ions, 10 to the negative 3rd. Okay, that's your typical store vinegar. Lemon juice, about 2.5. Stomach acid has a pH of 2. That means it's got a concentration of 1.0 times 10 to the negative 2 of hydrogen ions. 1 molar hydrochloric acid has a pH of 0. Concentration of hydrogen ions is 1 molar. You can have 10 molar hydrochloric acid. 10 molar hydrochloric acid would have a pH of negative 1. Remember, a factor of 10 change in the pH, or a factor of 10 change in the concentration, drives a factor of 1 change in the pH. Huh? Negative 1, yeah. You can. Concentrated hydrochloric acid has a pH of about negative 1.1.
How harmful is it to living organisms?
It will dissolve you pretty quick. Enough of it would dissolve you, yeah. I mean, it's same sort of thing, yeah. Yeah, basically. No. Changes in temperature drive changes to the concentration, the Kw value, but it's always going to stay balanced between hydrogen and hydroxide. Because every time a water molecule breaks apart, you get a hydrogen and a hydroxide. So it would still be neutral, really. The concentration of each would be equal. Yeah. It depends on what's dissolved in it, right? I mean, you can, yes, ocean water tends to be slightly acidic because of dissolved carbon dioxide, forming the carbonic acid, H2CO3. In fact, that's a big sink of carbon dioxide. The ocean is one of the largest sinks or absorbers of carbon dioxide. Hey guys, for carbon dioxide dissolving into the water. That's good for some animals which use that carbon dioxide, the carbonate to form calcium carbonate shells, but it's bad for others because it changes the pH and the organisms are fairly sensitive to pH changes. It denatures their proteins, and then they don't function correctly.
So is it a bad sign if your hot water heater is making your water turn into 9 pH level?
Wow, pH of 9 is really high for water that you would drink.
It's not drinking water, but more over
Yeah, that's unusual, especially for this area, because our water is so soft. There's not very many minerals in it. That seems very unusual. That sounds like there's some electrolytic process happening inside your hot water heater. Yeah, there are. In a couple of weeks we'll talk about it, but there are metal rods inside your hot water heater that prevent corrosion. And if there was an electric current, those rods could be corroding very quickly and could be producing something that could do that. When we talk about electrochemistry, we'll talk about that. Should definitely have it looked at. 9 is way well outside the realm of what we'd expect. So blood runs at about 7.5, slightly basic. A household ammonia cleaner is a pH of 12. Household ammonia cleaner is a pH of 12. Hydrogen ions of 10 to the negative 12. Okay? Now, in addition to pH, we can talk about the P of anything we want, because it's simply taking the negative log of it. So we can talk about POH. Jonathan. P stands for negative log of whatever the stuff is. That's what the P stands for. There's no word, doesn't mean anything. Yeah. We can talk about the P of S2O4. We can talk about the pK. We can take the P of equilibrium constant. And in fact, that is really common because we might want to talk about looking at water. Because hydrogen and hydroxides are balanced or related in a balanced way to Kw, we might want to take pKw to get the p-value of the Kw, right? So pKw would be the negative log of 1.0 times 10 negative 14, which would be 14. No, what this means, water is essentially neutral. It's balanced between them. But because it always maintains that ratio between the hydrogen and the hydroxide, it's very frequent for us to run across problems where we calculate one of the values, say the hydrogen, and from the hydrogen value we want to find the hydroxide value. Now we could use the Kw equation I showed you last slide, but if we already have, say, the pH, we may really want to take this Kw equation and simplify it to deal with a situation where we already have the pH or the POH. So if we take the P, or the negative log of each side, what we end up with is that pKw would equal pH plus POH. Since pKw we know is 14, we can, if we know the pH, find the POH of any situation, or vice versa. So if you're doing a problem where you're calculating the hydrogen ion concentration and then the pH, and then there's a second part that says what's the POH, well, you could do the long and extended route of saying, okay, I'm going to plug the hydrogen ion concentration in here, and then I'm going to divide it, and I'm going to calculate the hydroxide ion concentration, and I'm going to take the negative log of that. But if they just wanted the POH, you could plug your pH in here and subtract it from 14 to get your POH. Okay? This is only for water. This is in an aqueous solution. This is, the W here means water. So this is Kw for water. Now, the glass factory is a nice artistic glass factory. They're not manufacturing mass pieces. They do a lot of etching, right? They make fancy sort of shade glass, and they do etchings on the glass and stuff like that where it's frosted. And one of the ways that they do that, there are several, but one of the ways they do that is they use hydrofluoric acid. Hydrofluoric acid is a weak acid, but because of the way that fluorine ions behave, because of their really high electronegativity and electron affinity, the hydrofluoric acid will actually eat away at the glass. Hydrofluoric acid is frequently used to dissolve rock or mineral samples. It's used in silicon wafer production because it will dissolve the silicon masking stuff. So hydrofluoric acid is really useful for etching glass or doing stuff like that. highly toxic. It's absorbed through the skin and attacks the bones because the fluoride bonds very strongly with the calcium. So you have to be real careful when you use it, particularly at any kind of concentration. So 1 molar hydrofluoric acid it would be good for etching glass. It's dangerous. We want to make sure that it's, we want to know what's the hydrogen ion concentration of something like that. We want to be able to take a weak acid and calculate the hydrogen ion concentration. So here's an example of what some of the glass, if you just sort of brush some hydrofluoric acid onto glass, it eats away at the glass and etches it, produces this sort of etched, frosted, that's what I was looking for, frosted. That's one way. Probably industrially they just sandblast it. That would probably be a lot cheaper.
I met a guy yesterday who was like doing that.
Cool. You can also use bases. There's other ways that you can etch glass too. But so we know what the equilibrium is. The acid disassociating, right? The production of the hydrogen ions comes from the HF breaking apart into hydrogen and fluoride ions. It has a Ka value associated with it. We have a Ka 7.2 times 10 to the negative 4. Okay, so I'm telling you what that Ka value. Here's where we have to remember the setup. This reaction is taking place in an aqueous solution. We had a 1 molar aqueous solution of hydrofluoric acid. That means that in addition to the hydrofluoric acid, what else do we have in this solution? We have water. And we know that water can produce hydrogen ions. So we have to think to ourselves, well, which one of these is going to control the hydrogen ion production? And to do that, we have to think about this equilibrium. We have a Kw value of 1.0 times 10 to the negative 14. Which one of these two equilibriums is going to produce more hydrogen ions? The Ka value is 10 orders of magnitude higher. That means that the hydrogen ions produced here are going to be 10 orders of magnitude higher, roughly, or, it's approximate. We need to go through and figure it out. But we're going to get a lot more hydrogen ions from the HF than we will from the water. So, in this case, because the Ka is so much larger, we can neglect or we can ignore the contribution of the hydrogen ions to the water. Okay, from the water, I should say. So we don't really need to worry about this. What we do need to worry about is the hydrofluoric acid and how it breaks down. Essentially, we know the initial concentration of hydrofluoric acid, 1, and that these two values start out at 0. And I'm asking you to use the Ka value to solve for the equilibrium concentration. This is our typical sort of problem that we were just doing. What could we use to help organize ourselves? An ice diagram or an ice box. Okay? So we're going to have initial change equilibrium, 1.0, 0, 0. This is, yeah, should write this down. I'm gonna let you go through and solve this problem. Okay? You know how to do this. Solve for x. Okay? I want to know what is the concentration of the hydrogen ions. Okay, what's the concentration of the hydrogen ions? You know how to do this. This is the problem. This is a thing that we've done tons of times before. So take a few minutes right now. Set up that ice diagram. Do we have x values yet? So I got an x value of 0.027. So you can do this. You're going to have x, x, and negative x. 1.0 minus x, x, and x. Plug into the equilibrium expression and do the 5% rule. Say 1 minus x. Oh, 1 minus x is basically 1. And so then you have x squared equals 7.2 times 10 negative 4. Square root of this is that.
But you would never want to do the 5% rule if it was a strong acid.
No, if it was a strong acid, the 5% rule wouldn't work at all. This is a weak acid. Our Ka value is 3 or 4 orders of magnitude smaller than our initial concentration. That's an indication that we can probably use the 5% rule. Now, here's the king, right? This problem, what I was asking you to find was the pH. What do we have to do to this value to get the pH? We have to take the negative log of it. Okay? So negative log of 0.027, because this is the hydrogen ion concentration. So we want to take the negative log of it to get the pH. Press the, negative, not subtract, but negative, then log, then the number. 1.57. I don't think so, but I have to look. I can look. That's fairly acidic, yeah. If this was hydrochloric acid, it would be a pH of 0. So it's not nearly as acidic as that, but that's pretty acidic, right? We said stomach acid was like a pH of 2.
I thought stomach acid was the same as hydrochloric acid.
It is hydrochloric acid, but at different concentrations. Huh?
Isn't that weird? Everyone says that like milk is basic, but it's actually acidic.
Lactic acid.
Right, doesn't it serve as a buffer though?
I mean, it has a certain amount of buffering capacity, and it is less acidic than your stomach, so it would act to neutralize some of the acid in your stomach per se, depending on a whole host of. Milk is a complex substance. There's a lot of stuff in there. So, we definitely need to do some more investigations around the fish. Billy and Becky decided to take some of their fish to a specialist to investigate their fish. So they took it down to their local fish smeller to investigate what's going on. He has a lot of experience smelling fish. And so he believes that the fish may have been in an environment that was overly basic. So we're definitely going to need to investigate what could cause that. He's not joking. He's actually smelling the fish. I believe he really is actually grading tuna for sashimi. That's a real fish. It's real tuna. Well, tuna are huge. Tuna, the fish? No. Tuna grow to like 700 or 800 pounds. They're enormous. They're huge. Yeah, no, that would be. I mean, obviously there are different species of tuna. But go to the Monterey Bay Aquarium in their deep ocean tank. They have a little school of tuna in there, and those are the small tunas. They're not the giant ones, the albacores. But the skipjacks they're huge. Sushi. Maybe I'll go have sushi for